This is the sample test for the functions trigonometry test on limits and continuity, which is chapter 11 if you're following in the book. All right, so this is the first part of the test, and we're supposed to show all work neatly on this paper using proper notation. And remember, this is the calculator part, so we can use our calculator. Number 1 asks you to give numerical evidence to justify that the limit as x approaches 0 of tangent of x over x is equal to 1. They remind us in our calculator that we need to be in radian mode, and we need to include at least 6 values in our table. So I've just opened my calculator here. I'm using my Casio. I'm going to go into the table menu. This part would be the same. You'd be in the y equals if you were using your TI. Be sure whenever we're doing a fraction, we needed to be sure we were in radian mode for the tangent. And if this were on a TI, the x would pop up with a parenthesis, so you would need to be sure and close it. On my Casio, it doesn't matter so much. If there were any more terms on the top, I would need to also be sure the top of the fraction was in parentheses. So I've got that tangent of x divided by x, so I'm just going to hit enter and put that in my y equals, and then I'm going to make the table. I'm looking for the values as x approaches 0. So I'm not going to worry about what my table's telling me right now. I want to think about what I need to know in my table. If x is getting closer to 0, 0 needs to be sort of the middle of my table. So I want to think, if I were on a number line here with 0 in the middle, what values would be really close to 0 but above it? Really close would be like 0.001. A little less close would be if we got rid of one of the little zeros in there. 0.1, even a little further away. How about if we were over here on the left side of 0? They would be the same values but negative. Okay, so these are the things that I want to put in my table. I really don't care what happens at 0 because I'm looking for the limit here. It doesn't matter what happens at the actual value, just as I get closer and closer. And I want to see what's happening with y. So I'm going to come over here and I'm going to make my table, and I'm going to put in negative 0.1 as my first value. And I'm just typing and it's writing over these. Negative 0.01 and then negative 0.001. Now I need to be careful because it looks like my y values are just 1 in the table, but if I arrow over to them, I can see I really do have more than just a plain 1. So I'm going to write down what I have here. I have 1.003346. I'm going to write down a few more decimals than I normally would because I don't want to lose any accuracy here. So this one has 4 zeros and then a couple 3s. And then the next point down had, what's that, 6 zeros before I hit a 3. So I can tell, it looks like from this direction, that the closer my x value gets to 0, so as x approaches 0, y is getting closer and closer to 1. And that's what I was trying to do. I was trying to provide evidence to show that the limit was getting equal to 1. Okay, now I got to be sure that the same thing's happening for my positive values of x. So I'm going to go back up in my table, and I'm going to put in 0.001. And then I'm going to put in 0.01, and I'm going to put in 0.1. And I can see these y values are the same y values that I had from the other direction on the negative side. So I've got the 6 zeros, and then I've got 4 zeros before my first 3s, and then I've got 2 zeros before my first 3s. So it looks like coming this direction also, y is getting closer and closer to 1. By the way, if I put in x is 0, it does give me an error because that would create division by 0, but that's not going to affect us here. So the key is, as x gets closer and closer to 0, from either side, the left or the right, the y values are getting closer and closer to 1. So that's our numerical evidence. By the way, if you were using a TI to do this, you would need to go into your table set. So you need to go into second and then table set. And you change your independent variable over to ask instead of auto, and then it will let you type into the table just like I was able to type into the table for the Casio. Okay, so there was that one. Number 2 says, let's see if x equal the square root of 4 minus x, and then a plus 2 on the outside. For what values is c of x continuous? I should realize when it asks for what values of x is c of x continuous, I know this is a square root function, so it sort of makes a half a sideways parabola graph, something of this nature. Now it's going to be flipped around and moved and that sort of thing. But I'm really looking for sort of the domain of this function. The domain would be, where does this thing happen? So in order to be continuous, I have to avoid any problems. The thing in this graph that's going to give me a problem is I can't take the square root of a negative number. So whatever's underneath the square root is going to have to be greater than or equal to 0. If I were to solve this, I myself would move the x over to the right side by addition, and that would give me 4 is greater than or equal to x, or x is less than or equal to 4. That would be the domain, and that is also where c of x is continuous. If I wanted to write this in interval notation, it would be from negative infinity to 4. The infinity would get a parenthesis because we don't equal it. The 4 would get a bracket because we do equal it. Since I'm allowed to use my calculator on this part of the test, if I wanted to confirm this graphically, I could go into my graph and I could type in this function, the square root of 4 minus x, and then the plus 2 on the outside. I'm going to go to a standard window, and I can see the negative with the x has flipped me to the left. The 4 on the inside has scooched me 4 to the right. The 2 on the outside has scooched me up 2. But if I were looking at this point right here on my graph, the coordinates of that point would be over 4 up 2. So that's why I'm saying that x could be anything less than or equal to 4. All right. Moving down here to number 3, it says let m of x equal x squared when x is less than or equal to 2, or kx minus 1 when x is greater than 2. So that's a piecewise function. I'm supposed to find the value of k that would make m continuous. So I want a continuous function, and I'm supposed to find this value of k. So what number would work in there to make this continuous? Well, let me think about what I know about this function first of all. If I were to make a little picture of m of x right here, I have 2 branches. The first branch up here is x squared, and that is going to be graphed when x is less than or equal to 2. So I'm just going to put a little y-axis on here a little bit, a little x-axis marks. So x squared, that's a U shape with its center at the origin, and it goes like this. But I don't want the whole thing. I only want the parts where x is less than or equal to 2. So x was 2 right here at this end point. The coordinates of that point were 2, 4. I could figure that out by saying, what is m of 2? Well, m of 2 would mean to plug into the top the x squared branch, so I'd have 2 squared, which is equal to 4. In order for a function to be continuous, I have to have 3 things happen. First, the function has to exist at that point. Well, this one does. M of 2 is equal to 4. The next thing that happens to happen is that the limit as x approaches 2 from the left of that function would also have to be equal to 4. In this case, I can see from my picture, clearly that's happening because I'm on that left branch. The final piece that has to happen would be that the second branch, this function is kx minus 1. That line is going to have to meet up with this solid dot. So that line has a y-intercept of -1 and a slope of 2. So it's moving along up here. The question, a slope of k. So the question is, what slope do we need to have this happen so that it lines up and the open circle from the red function would fill in exactly landing where the blue dot was for the quadratic function. So I need for kx minus 1 to equal 4 only when x is equal to 2. So really I have k of 2 minus 1 is going to have to equal 4. So I have 2k, if I move the 1 over, would have to be equal to 5. Or k would have to be equal to 5/2. So if I make my slope 5/2, and I can check that right here on the graph, from this y-intercept I would go up 5 points over 2 points. That would put me right where I need to be so that my 2 graphs join up and I would be continuous. So really what I have happening here, the limit as x approaches 2 from the right of m of x is now also equal to 4, so long as my k is 5/2. All right, when I turn the page over and see number 4, it gives me one function, and then I notice as I look down the entire page, I have a lot of questions that deal with this one function. So I want to be sure my initial impression of this f of x is correct so that I answer all of these questions the right way. I also usually would probably like to scroll down and sort of see what is it I'm supposed to ask. In A, I'm supposed to graph it. In B and C and D, I'm finding the limit around 1. For E, I'm finding the limit around -2. Let me scroll down a little more. For F, I'm finding limits as x approach infinity. And then I'm doing some explanation about what's going on with the limit and the graph in part G. And in H, I'm stating the discontinuities and classifying them as asymptotes or holes. So right away, that should be a clue. This is going to be not your basic straight arrow graph here. I've got a little more going on. So the first thing I'm going to do is I'm going to put f of x into my y equals. Make sure when you're putting this in your y equals that you use parentheses around the top and parentheses around the bottom. So I graph that. I'm still in my nice standard window that I was in. Now my piece of graph paper that I have only goes from -5 to 5, so I'm really not going to want all of this window. I only want like this much of it. But that's okay. I can see some important stuff happening. It looks like I have a vertical asymptote going on here at x equals 1 and a horizontal asymptote at y equals 2. Let me put my graph back up there again. Okay, so what else do I have going on? I could make the table function to get some points. I could trace to get some points. So I'm going to go into the table for mine because I like to get my points that way. I'm going to change the setup of my table because the memory's just been reset to go from -10 to 10. If you had made a table on your TI, you might want to go to the table set and change your table back to automatic for the variables so that it will generate all the values you need in your table. So I make my table and I can see, let's start at x equals -5 because that's the first point on my graph. When x is -5, y is 1.833. So I just kind of eyeball approximately a little less than 2. At -4, I'm still at 1.8. At -3, I'm at 1.75. At -2, I have an error. What does that mean? That usually means an asymptote, but it can also mean a hole, remember. Sometimes I don't see that so well on my picture. If I wanted to find out, let me plot a couple more points here. So at -1, I was at 1.5. At -2, I was an error, and these guys were up here. Oh, I need my y-intercept. So let me get my y-intercept off my table as well. My y-intercept was 1. Oops, didn't mean to switch to green there. And then this guy was coming down here. And that's where I had my asymptote at 1. And then over on the right side of the graph, when x was 2, y was 3. And then I was getting closer, but I was laying on the positive side of the asymptote on the other side. All right, if I wanted to figure out the y value of the hole right there, remember I can on my calculator kind of fake it out. My table right now is asking me what happens when x is, where was the hole? The hole was at -2. If I typed in like a -1.99, I can see that my y value is close to 1.66. So that's about where I put the point. All right, so let's look at what happens here. On B, I'm finding the limit as x approaches 1 from the right. The limit as x approaches 1 from the means if I'm trying to find the limit at 1 right here. So as I'm approaching 1 from the right means my right finger is moving along the graph. What y value am I getting closer to? So where is the road going? That's what the limit is. Well, my y value looks like it's going up in the air. So I'm going to say that my function is approaching infinity. I don't want to say it equals infinity because I can never equal infinity, which means that my limit does not exist because the whole idea of infinity is it's limitless. All right, but on the right side, it's going up towards infinity. Then the next part C, asks me to find the limit as x approaches 1 from the left. So that means I have my left finger coming towards 1, and what's happening here is this one is going down. So for this limit, I would say that it approaches negative infinity, which does not exist as a limit because the whole idea of negative infinity is it's limitless. So for part D, I want to find the limit as x approaches 1 of f of x. I would say this limit doesn't exist, not because it approaches infinity, but because the left hand side does not equal the right hand side. Okay. It didn't really ask me that I had to write that explanation down, but it can't hurt. All right, question E says, showing any algebra necessary, find the limit as x approaches negative 2 of f of x. Well, the limit as x approaches negative 2 of f of x. F of x, I rewrote it down right here. So I have 2x squared plus 3x minus 2 over x squared plus x minus 2. So if I were to plug negative 2 into this thing, what I find is that I get 0 over 0, which is indeterminate. That's not a good answer. Indeterminate means I need to try to determine what the answer is. The way I'm going to do that is by factoring. So on the top, I'm going to factor. I have 2x, and my second set of parentheses would have an x. I need a 2, so it looks like if I put my 2 here with a plus and a minus 1 there, that's going to factor. I factor in my head. A lot of you guys don't do that. If you were going to factor this, let me come up here where I have a little more space. If you wanted to factor this without just doing it in your head, we would say I've got a 2x squared and I've got a minus 2. So I'm trying to multiply to negative 4x squared, and I have to add to the middle, which is 3x. So in order to multiply to a negative x squared, I'm going to need a negative x times a positive x. In order to multiply to 4, I'm going to have to do either 4 times 1 or 2 times 2. If I make 4 positive and 1 negative, I can multiply to negative 4x squared, and I can add to positive 3x. So now it's up to taking some GCFs here. So I take the GCF of my top row is 2x. So to figure out what goes up here, 2x times what gives me 2x squared? That's x. Over here, 2x times what gives me 4x? That would be a positive 2. Down here, x times what gives me negative 1x? That's a negative 1. And then my check, does the negative 1 times the 2 equal negative 2? Which yes, it does. And you can see that these two factors are the same factors I got when I just did it quickly in my head. Okay, to factor the bottom, I'd be looking for what two things multiply to negative 2 and add to positive 1. So I've got to do a 2 and a 1. And again, my 2 would have to be positive and my 1 would have to be negative. So looking at that, it looks like now I can reduce out this factor of x plus 2. So now I'm going to have the limit as x approaches negative 2 of just the 2x minus 1 over the x minus 1. At this point, I've eliminated or removed that problem spot. Now I'm ready to just plug in the negative 2 to evaluate the limit. So on the top, I would have a negative 5, and on the bottom, I would have negative 3. Negative 5/3 reduces to positive 5/3. So that's my limit. And if you remember back when we looked at the table, when I found the value that was close to negative 2, I had 1.66 something, and that's about 1 2/3. So this looks like it's making sense. It says, showing any necessary algebra on number f, find the limit as x approaches infinity. The limit as x approaches infinity of f of x. So let me scoot down my function a little more to make room. Okay, I want the limit as x approaches infinity. Remember with infinity, if I plug into my original function right now, I'm going to wind up with a whole lot of infinity over even more infinity. So when that happens, let me write down my function. I need to multiply the top and bottom by 1 over the highest power of x in the problem. The highest power of x in my problem is x squared for both of these. So I'm multiplying the top and bottom of my fraction by 1 over x squared. The reason that I do that is because now when I distribute, I'll have 2x squared over x squared. I'm going to jump ahead and show both steps at one time here, which would reduce to just plain old 2. So that was the first term on the top of my fraction. For the second term of my fraction, I'd have 3x over x squared. Those x's will reduce, and that will give me 3 over x. The last term of my fraction would become 2 over x squared, which isn't going to reduce at all. That's going to be negative 2 over x squared. On the bottom of my fraction, I would have x squared over x squared, which will reduce to 1. Then I would have x over x squared, which would reduce to 1 over x. And finally, I would have negative 2 over x squared, which is not going to reduce. It's still going to be negative 2 over x squared. Well, really, it looks like I just made this thing more complicated. How is this helping me? This is helping me because now when I go to take the limit as x approaches infinity, if I plug in 2, just stays 2. But 3 over x, as x gets bigger and bigger, this term will approach 0. Again, this one over here has x's on the bottom, so it's also going to go to 0. Down here, I have just a 1. In my fraction on the bottom, since there's x's on the bottom gets very large, it approaches 0. And then again on the end, that's going to go to 0 also. So my limit is equal to 2. Remember, I could tell this just by starting at the beginning of the problem. If I looked at this and I say, as x is approaching infinity, what's really going to matter is the big stuff. If I just look at the big stuff and reduce, I'm going to get 2. So I should know that my limit is going to be 2 before I even start the problem, but I have to show the necessary algebra to back it up, which is what I did with that multiplying by 1 over x squared. The other way that I can back up my answer here is what part G is it says, explain how the value of the limit as x approaches infinity of f of x relates to the graph of f of x. So what am I asking? As x approaches infinity, on our number line, infinity is way out. What's happening all the way on the right side of the function? So that's an end behavior of the function. In this case, if I scroll back up a little bit here to my graph, over here on the right, what's going on? I have an asymptote at y equals 2. So it makes sense that my graph should be approaching the asymptote because that's what's going on as x goes to infinity. So let me write that down. So the limit as x approaches infinity of f of x is equal to 2 shows the end behavior or horizontal asymptote at y equals 2. All right, the last step is to state the discontinuities of f of x and classify them as asymptotes or holes. Okay, remember the discontinuities of f of x? That's not going to involve a horizontal asymptote. It's only telling me the x values where we have problems in our function. And if I look back to this factored version, that's the easiest one to see on the page I'm on, I can see I have 2 problems. I'm not allowed to divide by 0. So if x is equal to negative 2, I'm going to have a division by 0. And if x is equal to positive 1, I'm going to have a division by 0. The x is equal to negative 2 was the one that canceled out, so that made my hole in the graph. The x is equal to positive 1 would not reduce out, so that's what made my vertical asymptote in my graph. This question also didn't ask this part, but we could classify this as being removable because it could reduce out, and this would be a non-removable discontinuity because it does not reduce out. So remember, when we have a big section like this and we have a whole bunch of bullets that go to one question, be sure that everything makes sense together. And in this case, all of my limits made sense together. They related to the graph, which went with the picture, which went with the factoring. Everything should correspond. If you're getting different answers from questions that are leading you towards the same thing, you know you're making a mistake somewhere. Okay, so now I'm turning over to the no calculator part. Number 5 has this crazy function, and the graph is shown, and we're trying to find the quantities if they exist, and be sure and read the directions. It says if it does not exist, explain why. So the first one here is the limit as x approaches negative 4 from the right of f of x. So where is negative 4? Negative 4 is right here. If it's from the right, that means where is my right finger going? Well, my right finger is going to y equals 1. So that's going to be the answer to this question for the limit. In part B, it asks me to find the limit as x approaches -4 of f of x. In order for this to happen, the left and the right have to go to the same place. So I already said that the right is up there at +1, but my left finger would be down here at -1. So that means that this limit does not exist because the left does not equal the right. And then the last thing dealing with -4 is to find f of -4. That's where is the solid point on the graph, if there is one. So the limit's where the road is going, whereas f of a value is where is the graph solid. And the solid point for this function was on the left branch, or down there at -1. So f of -4 is equal to -1. All right, question D asks for the limit as x approaches -2. -2 is right here on our graph. If I approach from the right, my right finger is going down here, which is a y value of -2. My left finger would also be going down there to the y value of -2. So the limit is the y value, which is -2. Question E asks for the limit as x approaches -1. -1 is right here on our graph. So my right finger, as I approach -1, is going to y equals 1. My left finger is also going to y equals 1. So the limit as x approaches -1 is that y value of -1. It doesn't matter that what I have here is a hole. I just care where the road is going, not where the actual point is. Where the actual point is what question F is asking. It's asking f of -1. And right here, there is no solid point, so f of -1 does not exist. It's a hole, and that's why it doesn't exist. Question G asks the limit as x approaches 1 of f of x. Well, 1 is an asymptote. As I approach 1 from the right, my graph is going up towards infinity. As I approach 1 from the left, my graph is also going up towards infinity. So both sides are approaching the same value. They're approaching infinity, but infinity is limitless. So it's important we say both things, that we approach infinity, but that does not exist as a limit, because the whole idea of infinity is that it's limitless. H asks for the limit as x approaches 4 of f of x. X is 4 is also an asymptote. On the right side of the asymptote, my graph is going up towards positive infinity. On the left side of my asymptote, my graph is going down towards negative infinity. So for this limit, I'm simply going to say that I do not exist because the left is not equal to the right. My answer in this should not involve any approaching infinity because my graph's approaching 2 different directions. That's why I don't have a limit in this problem. All right, on question 6, we're doing limits algebraically. We have to show our algebra. Be sure you're not being lazy and using your calculator to do simple math, because you won't have your calculator on your real test. Remember, with limits, if x is approaching 2, the basic thing to do is to just plug in the 2 and see what we get. If we don't have any problems, then we don't need to worry about doing any factoring or more work. So on the top of the fraction, I would have 6 plus 5, which is 11. On the bottom of the fraction, I have 2 minus 3, which is -1. 11 divided by -1 is -1. All right, on part B, I need to plug in x equals -4. If I have -4 and I cube it, that's going to equal -64. Plus 64 is going to give me 0 on the top of my fraction. On the bottom, if I plug in -4 plus 4, that's going to give me 0, and 0 over 0 is indeterminate. That doesn't mean I stop. That means I factor. Remember, I need to rewrite this limit as x approaches -4 because I'm still going to have x's in my problem. The bottom of my factors were x plus 4, so that's already done. The top is a sum of cubes, so I know my first factor is going to be the cubed root of each one with the same sign as I had in the problem. So the cubed root of x cubed was just x, the cubed root of 64 was the 4, and there was already a plus in between them, so that stays. My next factor was that big quadratic factor. To get that factor, I square the first term, which would give me x squared. Then I take the product of the 2 terms, which would give me 4x. I need to make the symbol, the minus, the opposite of whatever I had in the original problem. And then my last term is to square the last term in my first factor, and 4 times 4 is 16. This factor is always going to be positive because it's a square. So when I did that, it worked out nicely because now my 4's can reduce out. So really, I'm finding the limit as x approaches negative 4 of just the quadratic factor, x squared plus 4x plus 16. So that means I plug in negative 4 for my x. Negative 4 squared is positive 16. Negative 4 times negative 4 is positive 16. And the last term was also a 16. And 16 plus 16 plus 16 is 48. Okay, on C, I'm supposed to plug in x is 2. Now I can see already as I'm plugging in that I'm going to get division by 0. So on this one, I have 4 minus 9, which is negative 5 on the top. And I have 0 on the bottom. So I have division by 0, but this does not exist. There's no algebra that I'm going to be able to do that will have me reduce out this factor on the bottom because I had a number over 0 rather than 0 over 0. All right, in part D, I have the limit as x approaches infinity. So the first thing I want to do is I want to look and just see, can I figure out what the answer would be just by using common sense? We're looking at what infinity is going to win out here, the top or the bottom. Well, infinity cubed on the bottom is much more powerful than the top. When we have more infinity on the bottom, our answer goes to 0. So I know this right off the bat. I know my answer is 0. I'm going to write that down. And now I've got to do the algebra to back that up. All right. I like a number over 0, or a number over infinity, sorry, because that goes to 0. So this is the kind where I multiply by 1 over x to the biggest power in the problem. The biggest power was the x cubed. So I multiply the top and the bottom by my fraction by 1 over x cubed. When I do that, I have 3x squared over x cubed. And then I have x over x cubed. On the bottom, I have 5x cubed over x cubed minus 2x over x cubed. It looks a lot more complicated right now, but I can reduce each of these little fractions. And 3x squared over x cubed is going to reduce to 3 over x. X over x cubed is going to reduce to 1 over x squared. 5x cubed over x cubed will reduce to 5. And 2x over x cubed will reduce to minus 2 over x squared. What made this useful is that now when I plug in my infinity, 3 divided by infinity will be teeny tiny. 1 divided by infinity squared will be teeny tiny. 5 is just 5. 2 divided by infinity will be tiny. So I have 0 divided by 5, which is 0. And again, that's what I knew it should be from the first part. So I'm good. All right, question E. The limit as x approaches infinity of the square root of x minus x. Ooh, this one's a little more challenging. I'm going to think what would happen if I plugged in infinity. So it's not really, let me make this an arrow. It's not really a proper notation to say that's equal. I'm going to have the square root of infinity minus infinity. Well, this is an indeterminate form, infinity minus infinity. Do the infinities cancel each other out and go to 0? Or is one of the infinities more powerful than the other infinity? Well, this infinity has a smaller exponent, so it's not as strong as the infinity over here. So I can tell by looking at it that this guy is going to win out. And my answer should be that I approach negative infinity, which does not exist. Okay, but again, we have to show some algebra to back this thing up. So when I have square roots involved, what I want to do is to multiply. Let me rewrite the problem here. There is no top and bottom, but with limits with infinity, I like the top and bottom of a fraction, so I want to create a fraction, and I'm going to multiply by the conjugate of whatever I had. I had the square root of x minus x. I'm going to multiply by the square root of x plus x on the top and bottom. So this makes my problem much uglier. But again, I like ugly things with infinity. So on the top, I would be FOILing or multiplying this out. The square root of x times the square root of x is x. The square root of x times positive x, and negative the square root of x times the square root of x. Those are going to cancel each other out. And my last term would be negative x squared. That's the whole reason I like the conjugate, is it gets rid of my square roots, right? So on the bottom, I've got the square root of x plus x. Oh my, how has this helped me? Well, on the top, I still have infinity minus infinity, right? So infinity minus infinity, what's that doing? Ugh, I'm still not really sure. So if I'm not sure, I'm indeterminate at this point because I have infinity minus infinity squared, don't know what's going on. So this is one now where at least I have a fraction, so I can multiply by 1 over x to the biggest power in the problem, just like I did on the one above. So what does that do for me? Now I've got the limit as x approaches infinity. Remember, every time you still have x's in your problem, you still have to write down this limit as x approaches infinity. When I distribute, I have x over x squared minus x squared over x squared. On the bottom, I have the square root of x over x squared plus x over x squared. So let's do some reducing here. I'm still writing this word limit because I still have x's. I have x over x squared reduces to 1 over x squared over x squared reduces to 1. The square root of x over x squared. Remember, the square root of x is x to the 1/2. So the important thing to realize is that I'm only going to have x's left on the bottom. You can kind of think of it like you cancel a half of an x off the top with a half of an x on the bottom. So you're going to have 1 over x to the 1/2 or the 3/2. The important part here is that you get that there are more x's on the bottom, which means that factor will eventually go to 0. All right, so I've got x over x squared as my final thing, goes to 1 over x. So let's look at what happened there. Okay, so I've got x going to infinity. My first thing, as the bottom gets bigger, goes to 0. Then I had a -1. On the bottom, this guy's going to 0, and this guy's going to 0. So I have -1 over 0, which does not exist. So I know that my limit does not exist, and again, that's what I got up here in the top. I just had to decide, was it not existing because it was going to positive infinity or negative infinity? What's the end behavior of this thing? And I knew by logicking it out back at the beginning that my x to the first power was pulling stronger than my square root, so negative infinity is going to win out. You could also think if you plug in a negative large number, or a positive large number, what's going to happen there? And your answer would be negative. For example, if I plugged in, let's just throw in 100. So we'd have the square root of 100 minus 100 would be 10 minus 100, which is -90. So I can see the bigger that my... Okay, and number 7, we've got state the 3-part definition for continuity. You have to have this definition memorized. You will be asked for the exact definition on your test. So first of all, when we're talking about continuity, we mean, that for f of x to be continuous at x equals c, 3 things have to happen. So the first thing that has to happen is f of c must exist. That means when you plug in the number, you have to get a value for the actual function. The second thing is that the limit as x approaches c from the left of f of x has to equal the same thing you got for f of c in the first part of the definition. And then finally, as you plug in the limit as x approaches c from the right of f of x has to also equal f of c, the same thing you got in the first part of the definition. So this is going to be restated exactly like this on the test. All right, on number 8, we're supposed to sketch the graph of a function g, for which we have 3 things here. We've got the limit as x approaches -1 from the left of g of x has to equal 3. We've got the limit as x approaches -1 from the right of g of x has to equal 5. And also g of -1 has got to equal 2. So I got 3 things that need to go on. First, let me make a little axis. Okay, so there I have an axis now. First thing I was doing was as I approach -1 from the left of g of x. So here's -1. As I approach from the left, my y value has to go to 3. I'm going to make an open circle there because I'm not going to equal 3. I'm just, as the road goes towards x equals -1, my y value has to get closer and closer to 3. All right. Now I've got my second part. As x approaches -1 from the right, so that's going to be on the positive side of -1, my y values have to go to 5. So here's y equals 5, And the function, it could be doing anything I want to over here. It doesn't really matter. And then my final piece is that g of -1 has to equal 2. So that means the solid dot when x is equal to -1 has to be at a height of y is equal to 2. So I have to put a point on there. So what's happening over here on the right side? Let me get my highlighter. This could be any shape. This over here could be any shape. They have to have the two open circles on the top two pieces, and you have to have the solid dot at g of -1 equaling 2. But as far as the shape of the curves, they could be anything so long as they go towards the road value at that limit. All right, question number 9. This is another question where we have multiple things going on with the same question. We've got a big, nasty piecewise function, c of x, and then what am I going to have to answer about it? In part A, I'm looking at does we have a limit as x approaches 4. Now you notice 4 was one of our pieces, our joints to our pieces up here in the function. In part B, it's asking do we have a limit as x approaches 2. So 2 was another joint in my pieces. And then part C says, using the three-part definition, determine for what numbers x the function has discontinuities, and then classify them as point, jump, or infinite. So when I have a question with multiple parts, it's a good idea to look at everything I'm going to have to answer so I can put this in perspective. All right, so first I'm going to do part A. On this one, I'm looking for the limit as x approaches 4. So in a piecewise function, in order to have a limit as x approaches 4, I'm going to have to investigate the limit as x approaches 4 from the right of c of x, and then I'm going to have to say, does that equal the same thing as the limit as x approaches 4 from the left of c of x? In order to have a limit, both of these values will have to be the same thing. So 4 from the right. Well, 4 from the right would be when I'm greater than 4. This is the piece that's to the right of 4. It also equals 4, but that doesn't matter in the limit. So I'm looking at my function value. So I would be plugging in to 2x squared plus 16, and x has to be equal to 4. To evaluate this, the first thing I'm going to do is square the 4, which gives me 16. Then I'm going to multiply by 2 following order operations, and then I'll add those two pieces together, so the limit from the right is equal to 48. Now I need to do the limit from the left. The left is when I'm less than 4. X is less than 4 in this piece right here, which is a big, ugly rational function, but that's not going to matter. That's when I'm the left of 4. So I'm going to plug in. I'm plugging in, I have 4 cubed plus 4 times 4 squared minus 4 times 4 minus 16 all over 4 minus 2. Oh, I don't know why I put a 2 in there. Hold on. Up on the top of the function there. I was plugging in 4 for all of my x's. So what do we have here? Well, 4 to the 4th power, 4 to the 3rd power is 64. Then this right here, 4 squared, would be 4 times 4 times another 4 for the 4 out in front is another 64. And then we're going to subtract 16. Oh, I'm running out of room. There, I scooched that over. I'm going to subtract 16, and I'm going to subtract another 16. And on the bottom, I have 4 over 2, which is 2. So on the top, I have 64 plus 64, which is 128. And I'm going to take away 32 from that, which gives me 96. The bottom was equal to 2, and 96 divided by 2 is 48. So the answer is yes, it has a limit, and it's equal to 48. Because both the left side and the right side gave me 48, so I'm good to go. All right, part B says, does c of x have a limit as x approaches 2? So if we're looking as x approaches 2, I need to check what's the limit as x approaches 2 from the left of c of x. And then I have to check what's the limit as x approaches 2 from the right of c of x. And I have to see that those two things are equal. So the left of 2 is when I'm less than 2. So that would be up here in the top part of the function. That's the left of 2. So I'm going to plug in there. And I'm going to have 3 plug in 2 for x plus 2 gives me 6 plus 2, which is 8. Okay, so my limit as x approaches 2 from the left is fine. Now I've got the right side of 2. The right side of 2 would be when I'm greater than 2, which is this big ugly function again. So that's also the right of 2. So that's what I'm going to plug into. Now I can tell already just by looking at this that I'm going to have an x minus 2 on the bottom, so I'm going to have a division by 0. So I think I'm going to start out and just factor this as I go, because I know I want to reduce that and get rid of that x minus 2 on the bottom. If I did plug in by hand right now, I would wind up with 0 over 0, which is indeterminate, which is what tells me I definitely have to factor. So I'm going to come up here and do a little side work. I'm trying to factor x cubed plus 4x squared minus 4x minus 16. So I'm just going to factor using my area boxes here. So my GCF of the top row is x squared. That would give me an x on the top and a plus 4. And down here on the bottom, I'd wind up with a minus 4. And my check, does minus 4 times plus 4 equals negative 16? Yes, it does. So my two factors, now I've got an x plus 4. I'm going to write that down on the top of my fraction in my limit. And I also had an x squared minus 4, which I know I can factor some more, so I can factor that factor into x plus 2 times x minus 2. Another reminder that since I still had x's in my problem, I was still writing that limit as x approaches 2 from the right out there. Okay, the reason I like the factoring is because now I can reduce out the division by 0, so that's no longer going to be a problem. Once I've reduced out the division by 0, I can just plug in 2. So now I have 2 plus 4 of my top factor and 2 plus 2 for the second factor. So 2 plus 4 is 6. And on the second factor, 2 plus 2 is 4. And 6 times 4 is 24. So I've got a limit from the right. My problem is the limit from the left, which was 8, and the limit from the right, which was 24, are not the same thing. So the answer to my question is no. The left and right are not equal. So that's my answer. Okay, so the final thing in part C is using the three-part definition of continuity, determine for what numbers x the function has discontinuities, and classify them as point, jump, or infinite. Well, where do we have problems? Things we have problems with in math: when we have division by 0, that's a problem. When we have the square root of a negative number, that gives us a problem. If we've got the log of a negative or 0, that gives us a problem. Or if we have the joint in a piecewise function, that would also be a problem. So looking at this, I can see I might have two problem areas. I might have a problem at x equals 2. I'm not sure whether or not that's going to be a problem. I'll talk about it in a second. And I might have a problem at x equals 4. I'm not sure about that one either, because those are the two joints of my piecewise function. The other thing in this problem, I did have a division by 0, but that was at x equals 2, so that's already on my list. Okay, so let's look at what's happening here. What's happening at x equals 2? In order to have a discontinuity, we have to fail our three-part definition. The first part of our three-part definition was, does the function exist? So does c of 2 exist? Well, to find c of 2, sorry, I have a lot going on up here in this function, that would be when x equals 2 and c of 2 is equal to 8. Oops. So it passes the first part of our definition. Then I have to check, does the limit as x approaches 2 from the left of c of x? Well, I already found that. I found that up here. That was equal to 8. So that part passes. Then my final part of my three-part definition is, does my limit as x approaches 2 from the right of c of x equal the same number? Well, I did that over here, and for that one, I got 24. So this is where I fail. So this is a discontinuity at x equals 2. And what type of discontinuity is it? Well, I go from 8 to 24, so that's going to be a big jump. So that's a jump discontinuity. All right, let's look at x equals 4. The first thing I want to check is, does 4 work when you plug it into the function? So I need to look for where x is equal to 4. Where does x equal 4? That's right here, so that's the bottom piece of the function, so that's what I'm going to plug into. So I would have 2 times 4 squared plus 16. Well, that's 2 times 16 plus 16, which is equal to 48. So the first part of the definition passes. Then I've got to check, does the limit as x approach 4 from the left of c of x exist? And does it also equal 48? Well, I did that up here, and I know that that equals 48, so I'm good. Last part, does the limit as x approach 4 from the right of c of x exist? And is it also 48? And I did that up here, so that was 48. So at x equals 4, it's continuous. So that's not going to be on my discontinuity list. Okay, remember we could have 3 things. Point discontinuity is when we just have a hole in the graph. Jump is what we had right here when I had one piece that went to another piece and they didn't match up. And an infinite discontinuity would be an asymptote. So I didn't have that in this graph. All right, come into questions for anything you have left on this sample test, and good luck on